let's go back and review the ideas of the main idea of NP completeness. Again, it's the whole idea is on one slide. Okay, we've seen this slide 3 times. We're going to see it one more time last class of the semester. But I want to make sure we understand what the idea here of what we're trying to do. Okay, we want to be able to prove that a problem named mobility is a hard problem. What is our strategy to prove that mobility is a hard problem? We take a problem that we know absolutely certainly is hard. We know that SAT is hard. We know that 3 SAT is hard. We know that that vertex cover is hard. If we follow all of the stuff from so far in the semester, for one of these, okay, maybe we'll start with vertex cover. Vertex cover takes a graph as input. Suppose we have a translator that took the input of vertex cover and translated it into a problem that we want to prove hard, named mobility. We translate that into the input for mobility in a very, very special way. Well, first of all, vertex cover is a decision problem. So vertex cover only returns either a true or false. Mobility, whatever it is also going to be a decision problem. It's only going to return true or false. We want to be able to do this translation so that Bandersnatch of G is true if and only if mobility of Y is true. If we can do the translation so that everything is preserved, then we can return mobility of Y as the answer for Bandersnatch of G. And if so, this gives us a correct algorithm. Because if mobility of Y is always as fast, the same thing as Bandersnatch of G, then returning mobility of Y as an answer is perfectly correct. But what does this algorithm mean? If there was a fast mobility solver, that would give us a fast vertex cover solver. But what do we know about vertex cover? It is hard. We have proven it is hard. There is no fast algorithm for it. So if there is no fast algorithm for vertex cover, and there would be a fast algorithm for vertex cover if there was a fast algorithm for mobility, what did we do? We just proved that mobility has to also be hard. Okay? So long as this translation happens in some polynomial time, we know that vertex cover takes exponential time. The only way to make it that mobility has to also run in exponential time, because any algorithm that would faster would give me a faster algorithm than vertex cover, which we know can't exist. Any questions about that? Any questions about the thought process or logic that we're going through here? Is there any evidence that anyone's listening to me? I don't see any faces. I don't see hear anything. Is there any signs that people are out there?
Got it. Makes sense.
Got it.
Okay. Any questions? Okay, good. So then I want to go back to if that's clear, I want to go back to the reduction quickly that I did at the end of class last time, to make sure people understood the basic strategy of it. That's all that I'm going to kind of demand. I went through the details. Okay. I showed that the problem of vertex cover. What was the problem of vertex cover? The problem of vertex cover was we wanted to find a small set of vertices, okay, with the property that this small set of vertices, okay, includes at least one vertex of every edge. Okay, that these small set of vertices cover the graph. Okay, we were able to show Finding a big vertex cover was no problem. If we took all the vertices, we get a cover. For a small set of vertices, you are, to find the smallest set of vertices, that's a challenge. How much of a challenge we showed last time by showing basically an algorithm, a translation, where we translated the problem of 3 satisfiability into a graph G and a bound K, and said that if there was a way to cover this graph with this many vertices, then that meant that the original logic expression from 3-sat was satisfiable. Otherwise, it wasn't. And the translation we did basically went by, we constructed a gadget for each vertex, each Boolean variable of the SAT problem. And by putting edges here, we meant that you would have to make a decision, either pick V1 or not V1. And the same true for every one of the variables. We then connected them by logic clauses, okay? So that we had this property that if you had a satisfying assignment, okay, you would be able to, if this thing had a satisfying assignment, actually, that's interesting. I don't know quite what happened here. Hold on a second. Okay, if we had a satisfying assignment like this, like, let's say this, then what we knew was, because it was satisfying, each clause had at least one variable, okay, that was in the truth assignment. That corresponded to a way of covering one of the 3 edges connecting the triangle, so that we could complete the cover by picking the other 2. And if we did this, we will have completely covered, okay, all the edges in 2 times the number of clauses plus n vertices. And there was no way to do it unless the thing was satisfiable. So this was the clever translation, okay, where we translated the SAT problem into vertex cover, such that if you can cover this with this many vertices, the original thing was satisfiable. If not, it wasn't. Any questions about that reduction? Harkening back to the days before your break. Okay. Any questions about why that worked? Okay. So that reduction, and again, here was kind of the example, okay? That that if you had a satisfying assignment, you could have it would give you a cover of the right size. If you had a cover of the right size, it could only have used 1 vertex from each of these gadgets. It could use 2 vertices, only 2 vertices in each one of these gadgets, because that was your bound. And along the way, if it was satisfying, it had to take care of the uncovered connecting edge by being in one of the variables. Any questions about that? Going once. So I hope you realize now, you see why vertex cover is as hard as satisfiability. You should see that that's a pretty beautiful and complicated reduction. Oh my God, how could I come up with that? Okay. But once you've seen it, and once we have it, your job for proving things that are NP complete is going to be easier. Because if we want to prove that a problem is hard, all we have to do is to start from the right problem. Okay? We need a Bandersnatch and a Mobility. Okay? And we can pick any hard problem that as our Bandersnatch. Could be set, could be 3 set, could be vertex cover. Okay? And vertex cover looks quite different from set. So for certain problems, that may very well make it much easier to come up with a reduction for why something is very hard. Any questions about the strategy? Okay. Well, let's show now that once we have built all this machinery, we can maybe start to find some other problems that were hard. Okay, and we can maybe show them hard without going through quite the contortions we had to do for vertex cover. So one problem we talked about in here, actually even I think it may have been the first day of class, we talked about the movie star scheduling problem, which was a special case of this thing, which is called maximum independent set. If you remember the movie star problem, we had a bunch of jobs that were given by a constraint in time. And we wanted to find what's the most jobs we could take which didn't interfere with each other. Maximum independent set is a generalization of that, where for a bunch of different jobs, you have n jobs, and certain pairs of jobs, you can't take both. Maybe there's a conflict of interest if you work for these guys or that kind of people. Or maybe they're at the same time. Maybe there's a conflict of interest. Maybe there's some other reason why you can't do both. Okay? But we are faced with the problem of here, given an arrangement like this, we would like to find what are the most jobs that we can take that don't conflict with each other. Looking at this example here, what are the most jobs you can come up with that don't interfere with each other? It turns out that on this graph, only these two. If I take these two jobs, there's no edge between them. Is there any way to get a third job such that there's no edge between this and anything else? My claim is no. These four jobs happen to all be connected mutually to each other. You can't take any pair of both of these. And every one of these jobs. Oh, actually, could we? What about this? I think I just have a better example. Hold on. Is this something? Could I do 3 jobs?
Can you take the middle one?
Bunk, bunk, and bunk. Does everybody see that? That is, in fact, the maximum independent set here. Okay? So as you can see, this is a 3. Somebody email me to remind me to correct that in the slides. But does everybody see that that's that here, okay, I can do at most 3 jobs. Finding that was such a hard thing, I couldn't get it right before I came to class. Isn't that correct? Okay. But does everybody see what the problem is? Given a graph, okay, find the smallest number of vertices such that, find the largest number of vertices such that there is no edge defined between them. Any questions about that? Does everybody see why this is a useful problem? Okay. Now I'm going to tell you this problem is hard. Which of our, if we wanted to prove it is hard, which one of our Bandersnatches looks like the most related to this problem? Does anybody, we had SAT, does this look like a SAT problem? Does this look like a 3-SAT problem? Does this look like a vertex cover problem? See, someone thinks it looks more like a vertex cover problem. Why does it look like a vertex cover problem? Can someone articulate similarities? Okay. In what way does this look like a vertex cover problem? Well, what you're saying here is that one thing that's true is both of them are graph problems, so that's a start. Both of them are problems about picking things, right? Vertex cover. In one, we wanted to pick vertices, right? Vertex cover, we wanted to pick the smallest, the smallest set of vertices such that every edge was covered. Here, we want to pick the smallest number of vertices such that no edge is covered, the largest number of vertices such that no edge is covered, right? And when you think of it that way, well, then again, I encourage you to take a look at these things, okay? See if we can find a connection. I think people are saying it here. If I have, go back to my earlier example here of what a vertex cover is. If I take the vertices that are not in the cover, people are observing, all the vertices that are not in the cover have to form an independent set. Why can't there be an edge between two vertices that are not in the cover? Why do we know that if we take if the red is a vertex cover, why do we know that the things that are not the vertex cover, the blue, why do we know there can't be an edge between those two vertices?
Because one of them would have to be in the vertex cover.
If it was a vertex cover, it was covering every edge. This edge is not being covered. Does everybody see it? It could not have existed if this was a vertex cover. So what is the observation here? The observation is that for any vertex cover, what's left, if you take the set of vertices and delete anything from the vertex cover, you will get an independent set. Does everybody see that? And by definition, that has to be true. Okay, an independent vertex cover has to be vertices that cover all the edges. If I have an independent set, they can't have any edge between them. If I delete them, all the edges are still going to be there. The rest of the vertices will be the cover. So this gives us a translation. How can we write this reduction between vertex cover and independent set using our Bandersnatch mobility thing? What is Bandersnatch going to be? Somebody yell. What is my Bandersnatch? What?
Vertex cover.
Vertex cover.
I'm hearing vertex. You're saying vertex cover of G. And you're going to go do your mobility is going to be maximum independent set. Okay. And this takes as input. Is there an independent set in G prime of size J? I guess I really want to now ask myself this. G. You need to tell me what G prime is, and you need to tell me what J is. Okay, that's what the translation. What graph and what value of if we want to add, if we had a solver that given a graph G prime said, is there an independent set of size J? How would we use that to solve vertex cover? What is G prime equal to?
The complement of G if we take the edges that are not included in.
You're saying the complement? I don't see why to take a complement here. Okay. The argument here, I think, is that in this original graph, if this is a cover, then this is an independent set, right? So what is the translation here? I think I used the original graph. What is the size of the independent? If we want to know if there's a cover of size K, what is the size of the independent set that we're looking for?
V minus.
Okay, I am seeing N minus K. Does everybody see this is the translation that I want? If I want to know if my graph has a vertex cover of K vertices, that is exactly the same question of asking, does it have an independent set of size N minus K? Does everybody see that? This is the kind of thing I expect you to be able to do. Okay? Does everybody kind of see that this is an argument? That if I had a fast maximum independent set solver, I would be able to solve vertex cover quickly. I mean, my translation is just copying the graph and doing a subtraction. But so if I had a fast max IS, that would give me a fast vertex cover. But if there is no fast vertex cover, then this means that there's no possible fast max IS, because if so, this would be a fast vertex cover. Any questions? Okay. So basically, what am I saying? I am going to use the exact graph. See what the logic of it is. There's two levels. First, understand the logic on a picture level, and then look at the code. Okay? Basically, if a graph has a vertex cover of size K, okay, then what? Then all the vertices not in the cover are an independent set, right? A vertex cover of size K implies that there is an independent set of size N minus K. That's the green. If we want to make, again, finding a vertex cover, a large vertex cover is easy, okay? If we took all the vertices, that would be a vertex cover, okay? But what you call it? If we, if a vertex cover of size N means that you know how to find an independent set of size 0. That's not so hard either. Okay? The real question is, if you want to find the smallest vertex cover, that is the same, along the way you are finding what is the largest independent set. Any questions? Now, some people are saying they're looking at my code. Now, notice that the right way to think about an NP completeness proof really is like an algorithm. It's like code, okay? And some of you guys are complaining on the chat about the quality of my programming. You're saying, why did I use an extra variable here, G prime, when G prime was equal to G? I could have gotten the same thing by just putting G here and not making that transformate. I could have just written G here directly. That would have been fine. But conceptually, I like to lay out what are all the arguments here. Okay, this is how I like to express it. Okay, but you see that the debate of why did I have a G prime instead of not having a G prime is just a programming thing. It's not a logic thing. Any questions? It's a style thing. Any questions now about why maximum independent set has to be hard? Actually, hold on. Where do I go? Okay. Basically, if you are given a vertex cover Where was my vertex cover? Here. I'm assuming in this particular example, let's just take a look at it. It looks like this and this and this is actually take it, and this is my vertex cover. Okay. If I do this, I've got every edge has some red on it. If I take the blues, okay, this, and this, I have an independent set. So everybody see that this is an independent set, and this is a vertex cover. Any questions? Okay, good. Any questions about vertex cover? There is another problem, okay, that comes up in what you call it. So you're saying if there was no vertex cover, there was no independent set. If there's no vertex cover of the given size, there of size k, there is no independent set of size n minus k. Every graph has a vertex cover, okay? Take all the vertices. Every graph has an independent set, just take one vertex. But to find the largest independent set or the smallest possible cover, they are equally hard problems, as shown by that reduction. Any questions? Now, a clique problem is another interesting algorithm problem, okay? Which comes up in social networks. Let's say you're given a social network, like when you were in high school, okay? I imagine you guys were in high school more recently than me. At least when I was in high school, there were cliques of friends, okay? These friends hang out together. Everybody knew everybody else. What if you wanted to find, if you were on Facebook, you were Mark Zuckerberg, and you wanted to find what was the biggest group of people, all of whom are mutually friends? That is a maximum clique problem. Okay? Given a graph G and an integer J, does the graph contain a clique of vertices, okay, of J vertices, namely a subset of J vertices, here J equals 4, such that every pair of nodes, okay, in that subset defines an edge of the G? Thinking about it in terms of the friendship graph and social cliques, okay, maybe that should be clear what we're looking for. Okay, any questions about what a maximum clique is? Okay, people understand what the clique problem is? We're looking for the largest complete subgraph of a graph. Any questions? How would we go about proving it hard? Let's think about it. What would be our strategy? What is Bandersnatch? What is Bobilli? Does anybody have a candidate Bobilli? Or Bandersnatch? Well, what's Bandersnatch? Okay, I'm seeing anyone with a voice? What would be my Bandersnatch? Someone said independent set. Why is independent set what you want to choose as? What are our possible Bandersnatches? I've got set, I've got vertex cover, I've got 3 set, I've got independent set. Which one of these smells most like the clique problem? Someone with a voice.
Independent set.
Independent set. Why do you think independent set smells like clique?
In independent set, you don't have an edge between any 2 vertices. In clique, there is an edge between every vertice in the subset.
Okay, So you're saying that one of them, you're looking for a subset of vertices such that nobody's connected. And in another, you're looking for a subset of vertices such that everybody is connected, right?
Right.
So now now I understand why you want to do that. It looks like G, K. If we want to prove clique is hard, what is Bobilly going to be? What problem is Bobilly going to be?
The maximum clique problem.
Clique. And this takes us, as far as I'm concerned, to graph G prime. And it looks like an integer J. How are we going to transform a graph G, okay, into a graph G prime such that a clique in one is going to represent an independent set of the other? What are we going to do? Okay. I am saying you want to take the complement G. How do you complement G? Say nice G, nice graph. Okay. Complement is the operation that takes anytime there was an edge in G and turns it into replaces anytime there was G prime or G bar. The complement is going to consist of the edges that are not in G. Okay, and what would that be? Well, let's take a look at this. This is interesting because I think I may have. What do we have? We had these vertices. Okay. What you're saying to me is, if we complement it, what are the edges that we have? Bunk, bunk, bunk. Are there any other edges? There is an edge like this, and there is an edge like this. Does everybody see that? This is what the complement of G prime looks like, right? And what does this say? Okay, the claim is that if there is an independent set of size 3, bunk, 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 okay, in the original graph, then there is a clique of size 3 in the complement graph. Does everybody see that? So what you're saying here is this is going to be G equals K. This is the transformation. I want people to think about it. Do they see what we're doing here? If we complement the graph, then anything that was an independent set now becomes a clique. Okay? So asking, is there a clique of size K, is the same in the complement, is the same as asking if there is an independent set of size K in the original. Does everybody see that? The amazing thing here is, not amazing thing, these two problems are the same. You're saying, wait, where is the clique? If this is the complement, where do we see the clique? What is the clique in the complement? I need another color. Does everybody see that this is the clique in the complement? If this was an independent set in the original, when we complemented it, we got this as a clique. Okay? So finding a large independent set in G is the same as finding a large independent set in the complement of G. Any questions?
Are we supposed to be able to tell that there's a
clique of 5 in the original graph from the clique of 3 in the
Well, there is no clique of size. Okay. Well, let's just take a look at this thing. So this is, let's make sure we're reading this right. There was a clique of 4 in the original graph. Oh, wait a second. So now let me just think what I'm trying to do here. Okay. Actually, that's an interesting question here. Let's say this was G. Let's look at the properties of G. G here had a clique size of 4, right? It had an independent set of size 3, and it had a vertex cover of size 3. Okay, let me convince you of these properties first of all, and make sure I'm convincing myself. Does everybody see that what is the biggest complete subgraph here? Does everybody agree that the clique, okay, of size 4, which we're going to paint in is in blue? Maybe I won't even paint it. The clique in here is of blue. Okay. What was the biggest independent set in here? The biggest independent set was this. Does everybody agree? And the biggest vertex cover, the smallest vertex cover, which I'm going to call, what color should I make that? Orange. Was this. Does everybody see that, in fact, the orange vertices form a vertex cover?
Professor, I don't think your marker is showing anymore for some reason. After the blue dot you drew.
Oh, I had just, okay, that's not good. Okay, so let me try this thing. This is unfortunate now. Thank you for pointing that out. I had a beautiful picture there. Let me see if I can make this thing come back to life. You see it now?
Yes.
I think you see it now. Okay. Now, what is the point here on this one? We agree that if this is my original graph G, okay, over in here, G has a clique of size 4, which are the blue nodes. It has an independent set of size 3, which are the red circled nodes. And it has a vertex cover of size 3. Because anything that's not in the independent set has to be a vertex cover, right? Does everybody kind of see what this is saying? Do people agree with these properties?
Yes.
Okay. Now let's look at G prime. What is the properties of G prime? G prime, this is G prime. What is the size of the largest clique in G prime? Okay, let me redraw this a little bit just to hope that we get this right. I'll try to make it the way I want to do. Hold on. So we have a graph that the vertices should be that, this, this, this. What are the edges of G prime? Okay, I'm going to make it black, I think. The edges of G prime are this edge, this edge, this edge, this edge, and that edge. Does everybody agree that those are the only edges in G prime? People see that now? What is the size of the largest clique here? The size of the largest clique, I claim, is going to be of size 3. And what color am I going to make it? Let me make it, just because I'm going to use the complement properties, I'm going to make those vertices red. What is the size of the largest independent set? Or what is the size of the largest independent set? We also have an independent set, and we have a vertex cover. What is the size of the largest independent set in this graph? If I'm going to make an independent set here, I'm going to make this thing blue, just because I feel like it. Sorry, my machine looks like it's frozen again. No. If I want an independent set, I'm going to pick that vertex. I might as well pick this vertex and this vertex. And which other one? Any one of these other 3. Do you see that's going on? This tells me that the size of the largest independent set here is of, actually, no, it's not. It's got to be this. If I'm picking these, I can't pick any of those. The size of the largest independent set is of size 4. What is the size of the largest vertex cover in this complement? Okay.
2.
What?
2.
2, the vertex cover is anything that's not in the independent set. The claim here is that, in fact, the size of the largest vertex cover here is 2. Actually, let me make those, sorry, let me make that here. If I pick this vertex cover and this vertex cover, I will get every single edge in the graph covered. Does everybody see this? So this is in G prime, the complement. But what's the interesting point here? If we take a look at it, the size of the largest independent set in G is the same as the size of the largest clique in the complement. Likewise, the size of the largest clique in here, which is 4, is the same size as the largest independent set in the complement. This is what the relationship is, okay? If we have a clique of size K, if we have an independent set of size J, K in G, we have a clique of size K in the complement, and vice versa. Any questions about these relationships? So if you understand what I'm doing, it's kind of amazing. Vertex cover is vertex cover and clique and independent set are all different problems. They're all potentially useful problems. But in some sense, they are the same. If you could solve one quickly, you could solve the other ones quickly, and vice versa. Any question? Okay. Any questions about these ideas? I'm not sure. I don't get the sense I'm communicating it, but these pictures should make it clear. Any questions about that? Okay. Now we have, if you believe that, this reduction here shows that we've got another problem that can serve as a Bandersnatch in the future. Clique. Okay. Any questions? Okay, good. let's go back now. And I think I want to, boom, let's see if there's anything I want to say. Well, basically, I just said that whole thing. Right, I think I got that right. Right, okay, good. And boom. So the relationships are that if we have a vertex cover in G, the vertices minus that cover is a clique in G prime. And that if C is a clique in G, then V minus C prime is a vertex cover in G prime. This doesn't, I can't read very well, but I look at the pictures and I see it and I understand it. Any questions about that? Okay. If that's true, I want to do the problem of the day now. Okay. Let me see if I can get set up here. Boom, boom, boom. Okay. What is the problem of the day? The problem of the day says, prove that the densest subgraph is NP complete. What is the densest subgraph problem? I'm given a graph G. I'm given integers K and Y. And I say, does the graph contain a subgraph of exactly K vertices and at least Y edges? Okay. Can I find a chunk of the graph which has K vertices and at least Y edges? This is densest subgraph. If we want to prove densest subgraph is hard, what is Bandersnatch and what is Bobilli? Does anyone have a proposal here?
Can we use the clique problem that we use?
Can I use the clique problem? You say the clique problem looks like a densest subgraph problem in some way. In what way does they look the same?
Like when Y becomes like the complete, when it has like all the edges for K vertices.
So what you were telling me is that when you have a clique, the densest possible graph you can have is a clique.
Mhm.
In high school, that clique of friends no one liked. They were the densest group of people that they were in high school, right? Okay. So what do we do to prove what? What is Bandersnatch and what is Bobilli? You or somebody else. What is Bandersnatch and what is Bobilli?
Bandersnatch can be the dense subgraph and the clique can be Bobilli. And
Okay,
then
if that's true, let's think what you're saying here and let's see how this looks. Densest subgraph, KY. That's where the Bandersnatch goes. That's one way to put this down. Does this do what we want? Let's take a deep breath. Does this do anything that it wants?
I don't think it does, because all we know now is we can solve densest subgraph slow using clique.
Right, okay. This is an algorithm for solving densest subgraph, perhaps. Again, we haven't filled in the details. But if we fill in those details so the answers are the same, all that we know that we get an algorithm for densest subgraph that runs in time order clique. But clique we know is hard. So this gives us a slow way to solve densest subgraph if we did that. I think you've got your Bandersnatch and your Bobillis mixed up. Does everybody see this? This is just going to give you a slow densest subgraph algorithm. Because all we know about clique is that you can't solve it fast. You know, if I, again, if I need to do a simple task, let's say I want somebody to go to the store, and I've got somebody who's got airline tickets. They could go fly to Paris. Okay, assuming they can get through in time of COVID. Go, eat a crepe or whatever you do in Paris. Fly back and then go to the store, okay, which is down the block from you. But that doesn't mean that you needed to fly to Paris to do it, right? Here you're showing me a way to solve densest subgraph using Clique. This, I claim, is not going to help us because all we know about Clique is that it's hard. Okay? Does anyone want to make an alternate proposal of what the strategy is?
Bandersnatch is clique and Bobillia is densest subgraph.
Now let's try it the other way around. What if I said clique of G prime? No, let's just say G. I'm going to make clique is my G, J. Okay, I'm going to go erase that just because I want it to be proud. Now, what if I solve it using densest subgraph of G prime K Y? If I now, what does this mean? If I do find a way to do this thing, set these things up so that this is going to be true, okay, then if there's a fast densest subgraph solver, that would give me a fast clique solver. But if I have a correct thing here and I know that clique is hard and there's no fast way to be clique, this will be an argument that there's no way to solve densest subgraph correct at that point. Okay? So someone complete to me what G prime, K, and Y are, so that clique of this equals densest subgraph of that.
I'm going to propose G prime is G. K is J. And then Y is K times K minus 1 over 2.
So this is saying, if your densest subgraph can find me a subset of K vertices, such that between them, they've got, is this the right, by the way, let me see, if I've got two vertices, I want it to be 2 times 2 minus 1 or 1 divided by 2 edges. If I've got 3, I want 3 times 2 divided by, yeah, this looks right, okay? If I can find a subset of K vertices with K choose 2 edges between them, well, by definition, that has to be a clique of size K. How else, if I give you K vertices, how can you get K choose 2 edges from them except by there being a clique? Okay? So does everybody see that if I had a fast densest subgraph solver, the special case of looking for a maximally dense subgraph, the densest conceivable subgraph on K vertices, well, that finds me a clique of size J, okay? And since finding a clique is hard, there's no fast algorithm for this. There can be no fast algorithm for densest subgraph. Any questions about this logic? Do people see why this logic is the right one and this logic is the wrong one? It's very easy to get backwards, okay, when you're doing this kind of thing. But recognize what we're doing. That's kind of the order here is important, okay? Any questions about that?
So this doesn't prove anything or show anything about like whether we can actually do densest subgraph, right? Like we don't know whether there's actually an algorithm that works for that.
No. Well, first of all, can someone give me an algorithm for densest subgraph. Perhaps a slow algorithm for densest subgraph.
Well, I guess we could just try all subsets.
Try
of
all
K.
subsets of vertices of size k, all n choose k subsets of size k by backtracking or something like that. For each one of these, once I've built it, I now ask myself, how many edges does it have? If it has more y or more edges, I am golden. Okay? If not, I keep looking. And if not, I fail. So that is going to be something that is going to be something like n choose k-ish, which in the worst case is something like, for a large k, something like k over 2 is something like, k being n over 2 is something like 2 to the n, right? So there is, certainly you can find an algorithm for densest subgraph. I just gave it to you, right? But there is no fast algorithm. What we have just proved is that there is no fast algorithm for densest subgraph. If there was a fastest algorithm for densest subgraph, this here gives us a fastest algorithm for Clique. And there is no fast algorithm for Clique. Why do we know that? Because there is no fast algorithm for vertex independent set. Why do we know that? Because there is no fast algorithm for vertex cover. And why do we know that? Because there is no fast algorithm for vertex for set is preset. And why is there no fast algorithm for 3 set? Well, because there's no fast algorithm for satisfiability. And why do we know there's no fast algorithm for satisfiability? Because Skeena says it is the mother of all hard problems. That is the reasoning that we have just done. That's why there can't be a fast algorithm for densest subgraph. Any questions about that? So SAT is the original hard problem. That is the mother of all hard problems. Okay? Any questions about that? We're proving implicitly with this and all the logic that we've developed in class so far. We are proving in some sense that densest subgraph. You can't have a fast algorithm for densest subgraph unless you're going to get a fast algorithm for, if you had a fast algorithm for densest subgraph, that will give you a fast algorithm for SAT. And there is no fast algorithm for SAT. Any questions about that? Any questions about the strategy or the logic here? Okay, I want to make sure people understand this because I'm going to hit you with another hard reduction if you guys don't respond with interesting questions here. Any questions about that? Okay, on an exam, you have to start with from SAT. The answer is no. You can start from any of the hard problems that we have established are hard. Okay. Any questions? In theory, by the way, SAT will work just fine, but recognize that it's just a little bit, you want the translation to be as simple as possible. Okay. Just because it's easier for your mind to conceive a simple translation than it is something horrible looking. Any questions?
So now we can use dense subgraph to be the Bandersnatch, not just for this case where we're looking for like a complete subgraph, but for any.
So you could use densest subgraph to be your Bandersnatch. Okay. But I'm going to tell you, you could use densest subgraph to be a Bandersnatch. There's no reason why you can't, except I don't really think it's a great idea. Why don't I think it's a great idea? Okay. First of all, when you compare it to Clique, think about what you're doing conceptually with one of these translations. You're taking your Bandersnatch and you're translating every possible Bandersnatch thing into an instance of your mobility, right? if you're going to do a translation like that, you want your Bandersnatch to be as simple as possible, to make the translations you do with it as easy as possible. Why did my eyes light up when I saw 3-sat instead of sat? In satisfiability, you have to translate any set of clauses. For what you call it, for 3-sat, you only have to translate instances that have clauses of size 3. Does everybody see that the more restrictive the problem, the easier it is to probably do the translation from it, right? If I ask you to translate from Spanish to English, okay, this is in general a hard problem, right? But if I ask you to translate dirty words from Spanish to English, some of you may have that expertise, okay? That's a much simpler problem, right? So the more restrictive we make the hard problem, the easier it is to do the translation. Do you see what the point I'm trying to make is?
Yeah, I see, because we're
Clique has 2 arguments. This other one, densest subgraph, has 3 arguments. I'd rather translate from, given that they're so similar, this is the simpler problem to translate from. Okay, both of them can work, but artistically, I want to start from the simplest one. And I say Clique is simpler and more restrictive than densest subgraph.
So
Any questions?
is Clique just like a version of dense subgraph?
Clique is just a version of densest subgraph.
Okay.
It's not asking, find me a kind of dense subgraph. Remember, you can use the densest subgraph routine to say, find me a kind of dense subgraph, or find me a maximally dense subgraph, right? A densest subgraph solver has to solve both, right? A Clique solver only says, find me maximally densest solvers. Does everybody see that it's presumably easier to write a Clique solver than a densest subgraph solver, right?
Yeah, I see.
But Clique is hard. Clique is every bit as hard as densest subgraph. So that's why I would rather start from the, the simpler version, the more restricted version. Any questions? Okay. Why do we have K times K minus thing? How many edges does a clique have? If I have a clique, let's take a look at this thing. How many edges are in that clique? A clique on 5 vertices. If you count them, there are 5 on the outer ring and 5 in the star. Here are the number of edges. Okay. Y is 10. What is 5 times 4 divided by 2? That is 10. Does everybody see that asking, is there a subgraph of 10 vertices, of 10 edges and 5 vertices, is the exact same question of asking, is there a clique of size 5? That's what we're doing here. That's where that came from. Any questions of this? Any questions about anything about NP completeness so far?
So when you find a new reduction, it's kind of like almost going backwards up a tree, kind of like you're finding like the Bandersnatch is a subproblem of the Bow-Billy, right?
So what we're doing here is, let's think about it. What we're showing here, okay, so that's a good question. There's a little question here. You're trying to say which is, you're right in saying that there is a tree. Okay, sat sits at the top of the tree. 3-sat is down here. From 3-sat we did, I believe it was vertex cover. From vertex cover we did independent set. No, we did clique. No, I think we did independent set. From independent set, we did clique. From clique, we just did densest subgraph, right? So there is some sense that 3-set, we proved, is as hard as is harder in some sense than set, or at least as hard as set. Because if I could do 3-set quickly, I could do set quickly. Does everybody see that? Vertex cover is at least as hard as 3-set. If I could do vertex cover quickly, I could do 3-set quickly. Together, these things say that vertex cover is at least as hard as set is. Because if I could do vertex cover quickly, I could do set quickly. Independent set must be at least as hard as vertex cover. Because if I could do independent set quickly, I could do vertex cover quickly. That's what the chain of reductions is showing us. So in this case, you're right, that's kind of saying that this is a more general problem. Sometimes you can interpret these edges as being a question of generality, that this is a special case of this. But it looks kind of weird in general. Do you think that vertex cover is a special case of 3-satisfiability? This is an interpretation question, it's not a math question. I kind of have a hard time thinking of vertex cover as a special case of 3-satisfiability, right? Or 3-satisfiability as being a special case of vertex cover, okay? I do picture that clique is a special case of data, Any questions about that? What this reasoning means?
So I guess the easiest type of reduction to see is if the Bandersnatch is a more restricted version of the bowability, but it's not the only.
Bandersnatch is a more, if you have a hard thing, that is a more special case of that if you have that you're you have a hard problem that is a special case of what you're trying to show, then you're golden.
Right.
Okay, then the reduction is going to be very, very easy, right? Okay. Sometimes the reductions are not I don't think of it so sometimes they're special cases.
Mhm.
This was, I think, set the 3-set was a special case. And clique densest subgraph were special cases. The other ones I don't really think of as special cases, but they're transformations. Okay? Any questions about that?
Gotcha. Thank you.
Okay? Anything else? I have enough time here that I'm going to threaten you with a hard reduction if you guys don't respond. Okay? But this is the kind of thing conceptually I think you can do on an exam just fine. Okay? Any questions? Bang. Again, I went through this speech before. I'm not going to go do that. I'm going to show you one last hard reduction. Okay, so this is not one that maybe you're going to, I wouldn't expect you to figure this thing out. This is kind of a clever one. But it's going to show you again how you can translate a graph problem to a number problem. That is kind of an interesting one. The subset sum problem says that you are given, it's sometimes called integer, or special case of it's sometimes called integer partition. I give you a set of numbers, S, and a target, and I ask, is there a subset of numbers that adds up exactly to the target? I may have called something like this knapsack. Did I call something like this knapsack earlier in the semester?
Yeah, this sounds familiar.
Okay. So what is the idea here? The idea here is you have a capacity of stuff. you have, let's say this is, you want to buy items, you go into the store with this many dollars, and there are items for sale, there's one of each item, and you want to blow all the money that you have. Can you blow all the money you have, where you have this much money as your target, and you have individual objects, only one of each of the associated weights? In fact, for this problem, if you add these numbers together from the input, it does realize the target. For certain subsets, this can be realized. If my target was 3, I couldn't do it. If my target was 6, I couldn't do it. But for my target of 3,753, I can. Any questions about it? Okay, does everybody see what this problem is? Does everybody see that this is a problem that is a reasonable and practical problem? In general, we don't really have an algorithm for it, fast algorithm for it if the numbers are big. Okay, there's a little weasel word I'm going to make there. But if for big numbers, this problem, I don't know any algorithms for it. If we want to prove it hard, what is this going to be? Is subset sum going to be Bandersnatch or Bobilly?
Billy.
We want it to say basically subset sum, where I've got a set of numbers S and a target T. I need to somehow start from some other hard problem. Which hard problem smells most like subset sum so far? Probably you're going to say none of them smell too much like it. And that's why the reduction is going to have to be kind of tricky. But does any of them smell like this? Anyone? What if I told you I wanted to do vertex cover? In what way does this smell like vertex cover? Is there any way that this smells like a vertex cover to you? Well, why? How? In what way do you see a similarity?
We're kind of like choosing vertices to cover the entire set of numbers, which satisfies adding up to that sum, I guess.
Okay, so that's kind of the, I guess, kind of rough is the way that I wanted. We're thinking about analogies. We're not thinking about it. But yeah, subset sum was picking a bunch of numbers that add up to a target. Vertex cover was picking a subset of vertices that somehow take care of all the edges, right? Okay, maybe you don't see that yet. Let me show you very quickly a very clever transform for this. Okay, to do this, we are going to use vertex cover, and we're going to represent the graph not as a adjacency matrix, but by an incidence matrix. I use this word in one of the daily problems, although I may not have talked too much about it. What is an incidence matrix? It's going to have a row for every vertex and a column for every edge. And there will be a edge. If we have an edge between, this looks like vertex 4. If there is an edge between vertex 0 and vertex 4, that's edge 0. Note that this goes from vertex 0 to vertex 4. So in an incidence matrix, we are going to represent the graph by a matrix that is n. We use our usual notation from graph theory, n by m. Okay, and every column is going to have exactly 2 1s in it, and every row is going to be the degree of the vertex. This one had 1, 2, 3, 4 edges on it. 1, 2, 3, 4 1s. Any questions what an incidence matrix is? Okay. And to remind ourselves, vertex cover is picking a subset of a small subset of integer vertices such that every column we're going to have a 1 from every column. In this case, if we pick just vertex 0, okay, and vertex 2, does everybody see that 1 and 2, vertex 0 and vertex 2 make a cover? Because we get a 1 and a 1 and a 1 and a 1 and a 1. Any questions? Okay. What is the idea here? Okay, this is going to look a little ghastly, but it's actually not really as bad as you think. I'm going to think about each vertex. I'm going to take my vertex cover problem. Had n vertices and m edges. I'm going to create n plus 1 m numbers. And I'm going to create every number in base 4. Okay, which is going to seem a little weird, but I'll show you why. Okay. So what I'm going to say is for every vertex number is going to be a base 4 realization of each row of my incidence matrix plus a 1 stuck as a high order bit here. Okay, boom, boom. Let me clear this out now. Boom, 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 boom. What if I think of it? I'm now going to add a high order bit to every one of these rows. 1, 1, 1, 1, 1. Does everybody see that if I can interpret each row as a base 4 number? Why that is not clear to me, but what is that going to be? This is the 1, 4, 16, 64, 256, 1024. Okay, column. This number is going to be equal to 1024 plus 256 plus 16 plus 16. And that's what this number V2 is going to be. Any questions about the construction? I am also going to create a number for each column. Remember I said there's going to be n plus m numbers. I'm going to create n numbers, 1, 2, 3 up to n. I am also going to create m numbers, 1 for each edge, where it's going to also be a base 4 number. But my edge numbers are going to be all 0. If I have here something like this, something like this. See what I'm doing here? This is edge number 1, edge number 2, edge number 3, edge number 4. It's also going to be an edge number 5. Okay? So each one of these numbers is going to be basically just have one of my bits on. Okay? And I'm going to interpret it as a base 4 number. Why am I going to do that? Okay? What do I know? I've got, for any given problem, I've got a set of, what do I know? I've got a set of vertex numbers. And I've got a set of edge numbers. I'm going to need to create a target. But what target would represent a vertex cover? A vertex cover is going to occur when I have every single edge, okay, covered. Okay? What is my goal going to be? if I make this thing up, I claim if I pick a bunch of vertices, suppose I pick a set of k of these numbers that represents a vertex cover, what would happen if I added them together? Well, if you think about it, there's going to be k rows. If I add them together, in each column, if it's a cover, if I take two things that are a vertex cover, these two are a vertex cover. If I add those rows together, what am I going to get? I am going to get 1, 1, 2, 1, 1, 2. Do you see that if I add my V0 number and my V2 number together, they are going to give me this thing? Okay. And what do I know? I know that if I add up at each position, the no column can be greater than 2, because well, actually, if I take two of these vertex, if I add up the vertex numbers, adding up the entire matrix would come out to be what? I would get n 2, 2, 2, 2, 2, because of that's what if I added up all the rows together. If I add up these edge numbers together, what am I going to get? I would get 1, 1, 1, 1, 1. If I add all this together, what am I going to get? I'm going to get n 3, 3, 3, 3, 3. That's why I wanted base 4 numbers, by the way, so I don't carry anything. If I add up all my numbers I created, this is what I get. If I have a vertex number combo, a vertex cover, that if I add up the numbers corresponding to a vertex cover, which has of size k, I am going to have the outer thing is going to be of number is going to be k, because I'm adding up k of these things and they all have leading bits. And for all the edge positions, I'm going to have at least 1, 1 here. If it is a vertex cover, it's going to cover the edges. So what am I going to say my target is? My target T is going to be equal to K 2, 2, 2, 2, 2. Okay. And I'm going to say there is a vertex cover of size K if and only if you can get a subset of these numbers and these numbers that add up to this target. Why? Well, with these individual numbers, could turn a 1 by adding this number. I could turn that 1 into a 2. But I don't have enough to ripple through to the next digit. So by adding these, if I take any vertex cover, I take the numbers, if I have a vertex cover of size k, adding up those rows will give me a kth of high position, followed by a mix of 1s and 2s. By picking the appropriate edges, I have the freedom to turn any 1 into a 2. My claim is that you can find a subset of these numbers that will add up to that target if and only if you can the graph has a vertex cover of size k. Any questions? Think about it. It's kind of, again, one of these complex, beautiful, Baroque, but my God, how did they come up with this thing? But what this shows us is that finding a subset sum, if you could find a subset sum fast, you can find vertex cover fast, you can find bop, 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 bop fast. This is as hard as anything else. I know I've run over. I'm going to end it over here. But any quick questions about this reduction? Think about what I did. We've just added a quite different problem to our things. How do we find the edges in the matrix? Well, the edges correspond, we built this matrix. Each column corresponds to one of the input edges. Edge E2 represents this column. Okay, so we built the incidence matrix. We took the adjacency graph, built the incidence matrix, and then are interpreting them as numbers. And by looking at it the right way, we get a vertex cover, an integer partition problem. Any questions? How was the graph formed? The graph is the input. What are we doing here? We are showing vertex cover is the input. I am constructing a bunch of numbers, which I just described. I constructed a target I just described. Now, if you have a subset sum solver on these numbers, there will be a subset of numbers that adds up to the target if and only if there is a set of k vertices that forms a cover in that graph. So if I have a fast subset sum solver, I have a fast vertex cover solver. But there is no fast vertex cover solver. So that means that there is no fast subset sum solver. Any questions? If not, I know I'm over. I will end you here, and we will get this thing on YouTube, and you can look at it. Okay, thanks a lot.